Asymptotic formula comes to your rescue in this IMC 2024 problem 2. IMC basically refers to International Mathematical Competition, which is international competition for undergrads, right? And this is from last year. It was problem 2. And this problem can be easily solved if you know the asymptotic formula for hyperfactorial. There are also other ways like you can use like Riemann sum or some other things. But yeah, if you know the asymptotic formula, it becomes way easier. I guess you guys already know one of the popular asymptotic formula that this n factorial, like this is equals to square root of 2 pi n by e to the power n, and there are other terms like 1 plus and then in some order of 1 over n, right? Similarly, this is factorial, right? Now, what hyperfactorial means is like 1 to the power 1, 2 to the power 2, 3 to the power 3, up to n to the power n. This also has an asymptotic formula, which is Glaser-Kinkelin constant. This you can define it as e to the power minus zeta 1 minus zeta prime, minus zeta of minus 1 minus zeta prime of minus 1. Zeta of minus 1 is minus 1 over 12. So e to the power 1 over 12 minus zeta prime of minus 1. So Glaser-Kinkelin constant. Glaser-Kinkelin. Okay, let me write it properly. But doesn't matter. Constant. Okay. So I was saying this hyperfactorial, its credit formula is first of all Glaser-Kinkelin constant and then n times n square by 2 plus n by 2 plus 1 over 12 and then e to the power minus n over 4. Okay, so this is its asymptotic formula, and also there's this 1 plus order of 1 by n squared term, right? But as n goes to infinity, this just goes to 1, this just goes to 1, and then, yeah, when n goes to infinity, like we can just replace 1 with the other. So yeah, these are the asymptotic formulas, and this becomes really helpful in solving this problem. So let's see how. We have limit n goes to infinity, right? And here, since n is going to infinity, I can actually substitute this entire expression, which is okay. Let me just write this as hyperfactorial first. This adds of n, right, and then minus ln of root n, right? Also, I can actually write this as like as a single log, right? As a single log, I can write it like this as well, right? Okay, so now I can use, since n is going to infinity, I can also substitute Hn with their asymptotic formula, which is a and then n to the power n square by 2 plus n over 2 plus 1 over 12 and then e to the power minus n over 4, right, by square root of n. Okay, now if I use the n squared the square root, this will be a to the power 1 by n square, n to the power 1 over 2, n to the power 1 over 2n, n to the power 1 by 12n square, e to the power minus 1 over 4 divided by the square root of n. And then square root of n cancels with n to the power half, right? And the rest of the thing, now I can actually take the log, right? So that becomes ln a by n square plus ln n by 2n plus ln n by 12n square and then just minus 1 over 4, right? And now since this polynomial grows greater than log, we know that this thing just goes to 0, this thing also goes to 0, this thing also goes to 0, and minus 1 over 4. So we see that this limit is actually minus 1 over 4, and that's the answer from the official website. So over here, like, we saw that knowing the asymptotic expansion formula for hyperfactorial was super handy, and that just solved the problem in a few steps, right? That was so powerful. And like if you want to learn more, there's also a thing called superfactorial, right? Which is basically 1 factorial, 2 factorial, 3 factorial, this product up to n factorial. This also has an asymptotic formula. You can know that so that it can be handy or helpful when you are in some competitions. And yeah, so that was how you solved it. If you just used the asymptotic formula and then used some log property and then just some limit properties, and that's how we solve it. So that was it for today, guys. I hope you enjoyed this short video and then this powerful technique, and hope it's helpful for you sometime in your life. So see you in the next video.